All right, so this is test 2 review key. Um, Starting off the first problem, this is from chapter 4. Problems 1, 2, and 3 are all from chapter 4. Now, in this first one, this is largely just a calculator problem. We're given a set of data based on 6 randomly selected states, and the percent that have a bachelor's degree or higher, and the median income for that state. So we look at, we have two variables, x and y, and so we can find the linear correlation and the linear regression using just what we get from the calculator. Clear out this data first, sorry. Alright, so on our calculator, I'm going to put in L1 our x variable, so 24.3, 29.7, 30.6, 29.7, 31.5, and 37.3. Okay, oops, 0.3. And then in the second column, L2, we'll put the y variable, which is the median income in this case, so 49,800, 68,800, 60,000, 61,400, 59,700, and 79,800. Now, once we have the data into the calculator, there's two things we have to do, because one of the things that we run into with these specific calculators, and you may see it on if you have a different 84 calculator, and it really just depends on which variety of calculator we have. One of the things that we have to do first is we hit second, and right here above the 0 button, it says catalog, so we'll press that. This is our catalog of operations. Now, I don't know how I skipped through this. I wonder if there's a option. Nope, doesn't do that. Okay, so we just scroll down, and it's going to take a while. We have to get down to diagnostic on. There. We'll press enter, enter that again. This will basically, for whatever reason, we have to turn this on to get it to tell us the correlation coefficient R. But now, if we go back to stat, okay, edit was where we entered the data, and now we arrow right to calc, and we want linreg ax plus b. That's our linear regression. And not only does it give us ax and b, it's also going to give us our correlation coefficient R since we turned on that diagnostic setting. So X list, or X's are in L1, Y's are in L2. Keep arrowing down to calculate, or entering to calculate, and now we see our results. It says A is 2174.3, let's call it, and B is negative 3102.3. So, just writing this down underneath. Okay. So we got y equals A, which is 2174.3 times x. And then this will be a minus 3102.3. Okay. And so that's our regression equation. And we also want to make note R, which is 0.896 if we go to 3 decimal places. So with our data here, one decimal place is fine because y's is basically going to be a large number, and for this data is all like accurate to just 3 significant digits. But r, at least we can go out a little bit further. Now, so that's question 1. Question 2 says, what kind of correlation does the data have? Well, we look at our number r that we found, 0.896. And you might remember when we introduced this in chapter 4, we said, well, if r is in these different ranges, then we'll assign it a different word, whether it's positive or negative, and whether it's a weak, moderate, or strong correlation. And so this one, because it's positive and it's greater than 0.7, we call this a strong positive correlation. Okay, so that's all we have to do there. And now problem 3, an engineer wants to determine how the weight of a gas-powered car measured in pounds affects fuel efficiency, which is measured in miles per gallon. Here we are given a linear regression equation, and we want to predict the fuel efficiency of a car that weighs 3,220 or 3,250 pounds. Essentially, if x is the weight, then this value is going to be plugged in for x, and they just want us to calculate the y value, which would be the estimated fuel efficiency of this vehicle. So y will equal negative 0.00778 times 3,250 plus 46.6. And so we'll just do that in the calculator. So negative 0.00778, 2 sevens, there we go, times 3250, wow, I'm not hitting these buttons good, sorry, plus 46.6, and so that gives us about 21.3. So 21.3 miles per gallon. Okay. And so that would be the efficiency of that vehicle. All right. That takes care of page 1, the chapter 4 material. Then we get into the chapter 5 material. So problem 4, 3 events are represented from the given outcomes from choosing the numbers 1 through 10 from a hat. Thus, there are 10 possible outcomes from the selection. So 1 through 10, that's our sample space, as we called it. So we have 3 events, A, B, and C, that are defined. A is choosing a number that is even, which gives us 5 different outcomes, 2, 4, 6, 8, and 10. B, choosing a number that is a power of 3, so that's 1, 3, and 9, 3 outcomes. And then C, choosing a number that is at most 4, so 1, 2, 3, or 4 outcomes. So they've given a list of probabilities to find. Now, probability of A, since there's 5 outcomes and we know there's 10 possible outcomes, then we'll just take 5 out of 10, so that'll be 0.5 as our probability. Similar with probability of B, there's 3 outcomes there, so 3 out of 10, so that's 0.3, and probability of C, 4 out of 10. So those first 3 are pretty straightforward, and we should be fine with those. Now, where we start to make this a little bit more difficult is in the following, the problems after that, D through H, where now we're no longer just looking at the basic probabilities, but we have the and statements, the or statements, and the given statements. So one thing I would suggest just before we dive into this is let's go through and look at the terms that would be in these different AND statements, because the AND statements come up again and again, so we have to have this down before we can answer basically anything else on the rest of this page. Now when we say A and B, that means, okay, what numbers are in common between the outcomes in event A and the outcomes in event B? When we look at these two lists, there isn't any numbers in common. There aren't any numbers in common. So basically there's no commonality there. A and C, A is 2, 4, 6, 8, and 10, and C is 1, 2, 3, and 4. So 2 and 4 appear on both lists. So 2, 4 are in common to both of those lists. And then B and C, we have 1, 3, 9 for B, and C is 1, 2, 3, 4. So 1 and 3 appear on both of those lists. So each of those has two possibilities where both events are simultaneously true. A and B can never occur together based on what we're seeing. There's no commonality there. All right. So part D here, the probability of B and C, well, we've already kind of answered that. We know there's two outcomes for which B and C are both successful. So that's 2 outcomes out of 10. So 0.2. Now, when we have an OR statement, this is where we would like to use our addition rule. And our addition rule says we take the probability of the first part, which is B, plus the probability of the second part, which is C, minus the probability of the two together, B and C in this case. Now, luckily, we've already found all three of these things. We know the probability of B, 0.3. Fill that in. Probability of C is 0.4. And B and C, that's probability is 0.2. And so now we just combine these together, 0.3 plus 0.4 minus 0.2, and that gives us 0.5. Okay. And so that's our solution. Probability of B, and this vertical bar means given, and it indicates conditional probability. Okay. And in conditional probability, this means we want the probability that both occur, which in this case is the probability of B and C, divided by the one that's given to occur, which in this case is C, whichever one comes second in this probability statement. Okay, because when we say the probability of B given C, that means we know that C has occurred, so we're considering that likelihood. What's the probability that B also occurs? And that kind of utilizes the multiplication rule. It is based on the general multiplication rule, just kind of solved for a different term. But now that we know the formula to do that, we can still just plug in the values that we already used. The probability of B and C is 0.2. And the probability of C is 0.4. And now we just divide those. 0.2 divided by 0.4 gives us 0.5. Right. And so the rest of these are more or less what we've done already. Probability of A or C. This is again our addition rule because of the OR statement. So just like we did in part E, we'll do the same thing here. So that means it'll be probability of A plus probability of C minus probability of A and C. Now the probability of A, we know that's 0.5. And the probability of C is 0.4, so we have that. 0.5 plus 0.4. And then we need the probability of A and C. Well, back up here we said, well, there's two numbers in common between the two events. So that's 2 out of 10, or 0.2. So that's what we'll end up subtracting. And so that ends up giving us 0.5 plus 0.4 minus 0.2, so that's 0.7 is the probability that either A or C or both are successful. And the last question, H, probability of A and B. If we go back up here, now notice now we've used all three of these things by this point, or this will be the third one that we use. A and B have no commonality, so the probability that both of them occur simultaneously is 0, okay? Because they just don't have any outcomes that are in common with each other. All right. Moving on to problem 5. Now, this is kind of a similar set of questions, but now given in a different context. 4 is kind of our classical probability problem where, everything is equally likely to occur. We're just as likely to select a 1 from this hat as we are from any other number. Okay. Now this is what we would call our empirical probability, where now we're just calculating probabilities based on just the data that we've collected. Like in this case, we're looking at a department store that offers 3 colors of appliances, and we're looking at 2 appliances in particular. And we could have made a bigger table, but I just wanted to keep it simple. All right, so in this table we have the 3 different colors, the 3 different finishes that are available in the 2 appliances, and we have row and column for totals as well. So looking at this, we understand 50 total appliances are available at this department store, which is largely becoming a thing of the past, department store. I guess Best Buy would be a better example nowadays. What is the probability that an appliance selected at random is a dishwasher? Well, we look at dishwashers. There's 25 of them out of 50 total appliances. So 25 out of 50, and that just calculates out to being 0.5. Okay. What is the probability that an appliance selected at random is stainless steel colored? Well, we look at the stainless column. There's 24 of those out of 50. So that we can just divide those, and that calculates out to 0.48. So these first 2 questions are basically just a simple probability. What's the probability of this being selected versus the probability of this being selected? And it gives us 1 of each type, basically. But now we start in parts C, D, and E, looking at our other variations on probability, kind of like in that we just looked at over here, where we started off with the simple probabilities, and then we started to look at the different combinations. So these 2 problems really mirror each other, but in an entirely different scenarios, where one was classical and this one's now empirical. So what is the probability that an appliance selected at random is both white and a dishwasher? And I've underlined kind of the key word here, which is and, meaning we want the intersection of those 2 things. So white and a dishwasher. So we look at our row on dishwashers and our column on white, just 2. So only 2 appliances that fit both criteria out of all 50 that are available. So that ends up being 0.04, I believe. So that's our probability. Now in part D, the probability that a randomly selected appliance is stainless steel or a refrigerator. So now with or, we have a combination of 2 events. So I'm going to identify this as event A and event B, just for simplicity's sake. And this goes back to our addition rule. Let me write that down here. Okay. Which is P of A or B is equal to P of A plus P of B minus the intersection P of A and B. So we go back to our table. The probability of A, that's stainless steel. Well, actually, we've already found that right here. Stainless steel is 0.48, or, well, 24 out of 50 is probably a better way of saying that. The good news is all three of these will be out of 50, so we just really need the number 24. Okay, how many refrigerators do we have? Well, we come back up to our table. There are 25 refrigerators. And then finally, we need the intersection of stainless steel refrigerators, which now, looking at the stainless column and the refrigerator row, that's 13 of those that meet both criteria simultaneously. So we have to take away 13. Essentially, that's the number that we've overcounted by, because those 13 appliances already appear in both of these lists, or both of these categories. So we've overcounted by 13. So we have to balance it out. So 24 plus 25 minus 13, that gives us 36 out of 50, which is 0.72 probability. Okay, now in this last part, we have our given statement. The given, again, indicates conditional probability. Okay. So I'm going to assign this B and A. The reason I do B and A is that the given one being A is, at least in my mind, that works more logically. And if you just want to write down the formula, that's fine. So this is probability of B given A. Now, again, the formula is we want the combination of the two, B, A and B, in this case. And then whichever one is given A is the one on the bottom. So probability of both A and B, which is that is a dishwasher and it's black. Okay, this is my dishwasher at home. There are 12 of these that fit both criteria. So 12 out of 50. And then the probability that it's a dishwasher in the first place, well, there's 25 dishwashers total. So that's 25 out of 50 again, which we already did that in part A. And then what we're going to find is that the 50s basically cancel out of this equation. And we could do that with, if we're dividing two fractions, we know we take the second fraction, flip it over and multiply, and maybe this makes it a little bit easier to see why the 50s cancel out. But ultimately we end up with 12 over 25, whichever way we look at it. From here, just canceling out the 50s, or from the idea of changing it to this multiplication problem where you multiply by the reciprocal of the denominator. But either way, that works out to be 0.48. Okay. Moving on to problem 6. Now, problem 6, suppose we have a small bag of jelly beans. In this bag we have 40 red ones, 33 blue ones, and 27 purple ones. I guess I could have given them actual flavor names, but we'll go with colors, I guess. What first thing we need to know before we can do anything here is how many total jelly beans are in this particular bag. Well, we know there's 40 that are red, 33 that are blue, and 27 that are purple, but that does add up to 100. And while they may not give you a sum of 100 on the exam, it should be a relatively easy number to work with. But ultimately, if we need to, we can use the calculator to do this. So, all right. Now, one of the key things, and this is why I have problem 6 and problem 7 on the same page. Essentially, they're the same type of problems because they both utilize the multiplication rule. But there are key phrases to look for: without replacement, and here in 7 I mentioned that it's with replacement. Okay. Now, without replacement means it's the general multiplication rule. And this is dependent events. Okay. So that's kind of the key. That means if we're not replacing the jelly bean after we select it from the bag, that means the probability is changed on the second draw, on the second selection. So if we look at 2 blue jelly beans, our first blue jelly bean, we know there's 33 total in this bag out of 100. But now, if we've removed that blue jelly bean and we haven't put it back into the bag, so without replacement, how many blue jelly beans do we have now? Well, there's 32 left because we took one of those away. And also, there's no longer 100 jelly beans. There's 99 jelly beans. So 32 of the remaining 99 are still blue jelly beans. And so that's why we say these are dependent, because the probability changes now after our selection on the first jelly bean. And now when we multiply these fractions, we multiply straight across. So that'll be 33 times 32 on top and 100 times 99 on bottom. So 33 times 32 is going to give us 1,056, and 100 times 99 will give us 9,900. And so we want to divide those. 1,056 divided by 9,900. That will give us about 0.107. And so that's our probability that we could select 2 jelly beans at random and they'll both be blue. About 11% chance. All right, and now in problem B, we mix that up a bit, and we say, okay, what if we want the first one to be purple and the second one to be red? And we go back and look, okay, well, there's 27 purple jelly beans to begin with. So we know in that first selection, there's a 27 out of 100 probability that we would select a purple jelly bean. And for the second one being red, there's still 40 red jelly beans in this bag because we haven't removed any of the red ones yet. But because we did remove a purple one, there are only 99 jelly beans left in this bag. Okay? And so, similar to what we did in the last example, we'll just multiply across. So we'll take 27 times 40 in the numerator. And that gives us 1,080, and 100 times 99 is still 9,900. That didn't change. And now we divide 1,080 divided by 9,900, and it's just going to be a little bit larger than the last one. This is about 0.109. And if we round these to 3 decimal places for these probabilities, that's perfectly fine. We don't really need to go any further than that. This is, at this point, we're just demonstrating that we understand the question. Like, okay, I know that you've gotten the correct answer because you've got the correct answer to 3 decimal places. Okay. So 7 now, like I said, it's a similar problem, But now this is done with replacement. That means it can repeat. I need to update this question because I don't think people buy digital albums from iTunes anymore. So I'll try to update that for the exam, make it more realistic. So anyway, but maybe we just download the album and just play the album. That's probably more realistic. But this particular album has 11 songs, and we actually, turns out we really like 7 of them. Okay, but now remember, the songs can repeat as often as possible. So if we're playing 2 songs at random, now with replacement, before we get any further, essentially means that the events are independent. Okay, which means the probability will not change from the first play to the next play. So when we play that first song, we like 7 out of the 11 songs. So 7 out of 11 chance we like the first song. Now second, because that first song can repeat, that means there's still 7 songs we like and still 11 songs that may be selected for that second play. So now it's unlikely, I don't think most people play an album with replacement. We may put it on repeat, but that means after they play all 11 songs, we'll go back through the list again. But so maybe this is not a realistic example. But anyway, so 7 out of 11 on the first try, 7 out of 11 on the second one. So putting that together, that is 49, just multiplying across. 7 times 7 is 49. 11 times 11 is 121. And then we'll just divide 49 by 121. And so we get 0.405. So better than a 40% chance we'll like both of the first 2 songs played. Well, part B says, well, similar scenario, but now we don't like either one of the songs. So the first question is, because this was not given in the information, how many songs do we not like? Well, if there's 11 songs and we really like 7 of them, that means the other 4, maybe we don't like them as much. Maybe they're just okay. We know not every song on an album is a winner. So there's 4 songs that maybe we don't like as much out of the 11. And on the second play, same situation. Any of those 4 songs can be played again. And so 4 of 11. So 16 out of 121, and then we'll just go through and calculate that. 16 divided by 121, so about 0.132. So a little bit better than 13% chance that we don't like either one of the songs. We can just hit the next button. Anyway, so part C now, this changes things up a bit from what we saw in problem either of the previous parts of these 2 problems, which is now what is the probability we like at least one of the songs. Well, when we see at least one, this tells us that this is going to be complementary probability, which is, we haven't really seen this anywhere else on this exam to this point, on this review to this point. And this may be the only time it shows up. I don't remember. It actually shows up again on problem 9. We'll get to that in a second. But complementary means while we can find this probability, it's kind of a challenge, because when we say we like at least one, there's really 3 different scenarios tied up in that one statement. We like the first one, but not the second. We like the second one, but not the first, and we like both of them, because that also counts. That's really 3 things that we would have to find and add their probabilities together to get this probability. And if we want to do that, that's an option. Excuse me. But the easier way, and probably the better way, and kind of the intended way that we would like to approach this problem, is to use this complementary problem to our advantage. What is the opposite of liking at least one song? Because the complement means basically the opposite scenario. Well, it turns out the probability of liking at least one song is that we don't like either song. Okay? And the way that we know that complementary probability works is that for the opposite event, it's 1 minus that probability. Okay? And so now the question is, well, what's the probability we don't like either one of the songs? Well, we just calculated that in part B. So we're going to take this probability we found in part B, 0.132, plug it in here. So we just had to find 1 minus 0.132, and that turns out to be 0.868. Okay, so in this one, that's probably the easiest approach, is just knowing that the opposite of liking at least one is that we just don't like either one of them, like we like neither. And that gets us back to what we had already calculated in B, so we just take that result and subtract it from 1 to get our answer. Okay. So we move on to problem 8. Now in problem 8, a game is suggested to us at a party. This is from now chapter 6, these last two problems. A person has the numbers 1 through 10 in a hat, and we will pay them $1 to play. If we draw a 1, 2, 3, or 4, we will then pay them an additional $1. If we draw a 5 or 6, we will win $1. If we draw a 7, 8, or 9, we'll win $2, and if we draw the 10, we'll get $3. So, as far as the outcomes go, we've kind of broken them down into 4 possibilities, because if we draw a 1, 2, 3, or 4, the same thing happens in each of those cases. So we'll call that our first set of outcomes. If we draw 5 or 6, something else happens. Okay, that's our second set of outcomes. If we draw the 7, 8, or 9, a third thing happens. That's our third set of outcomes. And if we draw the 10, then that's a fourth possibility. Now, when we talk about our net winnings, we have to consider the fee or the bet that we make at the beginning. In this case, we will pay them $1 to play. So we're spending $1 up front. Now, if we happen to draw a 1, 2, 3, or 4, we will then pay them an additional $1, meaning now we've given the person hosting this game $2, and we have now lost $2. Okay? Now, we pay them $1 up front, and if we draw a 5 or a 6, we win $1. Well, at that point, we're basically just getting our $1 back. So we now have neither won nor lost any money in this process. 7, 8, or 9, we win $2. Well, again, we paid them $1 to play in the first place, so if we win $2, we've only gained $1 from where we were initially. Okay, we paid $1, got 2 back, so now we're up $1. And finally, if we draw the 10, it says we win $3, but again, we paid them $1 in the first place, so in reality, we've only won $2 beyond what we initially had before we played this game. So when we talk about the second column with this net winnings, we have to consider that that $1 we paid up front as part of this calculation. So essentially we're taking each of the results, -1, +1, +2, and +3, and subtracting that $1 from each of those 4 outcomes. Now, what is the probability that we would have this particular outcome of losing $2? Well, that happens for 4 different numbers out of the 10 that are possible. So this is 4 out of 10, which is 0.4. You don't have to write down the 4 out of 10 there, but this is just indicating that, okay, this is how we got this number. So 5 and 6, that's 2 numbers out of 10, that's going to be 0.2. 7, 8, 9, that's 3 numbers out of 10, so 0.3. And the 10, that's 1 number out of 10, so 0.1. And now in our last column, we want to find x times p of x. So we're just going to multiply these two numbers for each row. Okay. So negative 2 times 0.4 is negative 0.8. 0 times 0.2 is 0. 1 times 0.3 is positive 0.3. And 2 times 0.1 is positive 0.2. Okay. So that completes our table. Now we can approach part B. What is our expected value for playing this game? Well, our expected value can be found by adding these 4 numbers together in this last column. Now, so this result down here will be our expected value. Now if we add these together, negative 0.8 plus 0.3, not negative, I'm sorry, plus 0.2, then we get negative 0.3. Now, remember that this amount, since we're talking about paying them in dollars and receiving dollars for winning, so this is negative $0.3. So we might say our expected value is to lose $0.3, which is means basically we're losing 30 cents on average each time we play this game. So now the question is it a fair game? No. What would make a fair game? Well, as we mentioned in class, a fair game is one where the expected value is 0, where we neither expect to win nor lose on average. This is definitely not a fair game because on average we expect to be losing. And in the long run we expect to be losing. Okay, so not a fair game. So 2 parts to that question. All right, and finally, question 9. A recent study found that 60% of teenage consumers receive their spending money from part-time jobs. 20 teenagers are selected at random. Okay, so N, that's our number of trials or sample size. So we selected 20 teenagers at random. Okay, so that's who we're using for this. P, this is the probability of success. Now, the probability that we successfully find a teenage consumer that earns their spending money from a part-time job, that's our 60%. So our probability, now we won't write down 60%, but we can put down 0.60. Now Q is our probability of failure. Q, remember, is equal to 1 minus P. So if we already found P was 0.60, then we'll just take that away from 1. So Q is going to be 0.40. Okay. So those first 3 numbers were basically, we can discern what's going on there from the stated question. Or not even the stated question, just describing the study. We found 60% of teenagers got spending money from part-time jobs, and we picked 20 at random that we wanted to just determine how many have part-time jobs in that group. Okay, so the mean, now this is going to be a formula, and as we mentioned in class earlier this week, the mean is calculated by taking n times p, so we know n is 20 and p is 0.60. And so multiplying those together, 20 times 0.60 gives us 12. So on average, we would expect 12 of those 20 teenagers to receive their spending money from part-time jobs. Teenage consumers. So that's that. Moving to the next page. We have 4 more parts in this problem still. So E, we want to find the standard deviation. So the formula for the standard deviation is n times p times q under the square root. As always, our standard deviation is the square root of the variance, but we don't really use the variance for anything just yet. That'll be in a later stats class if we take one. N is 20, P is 0.60, and Q is 0.40. That's what we found on the previous page, so we're just plugging in these numbers. So we're taking the square root of 20 times 0.60 times 0.20, hit enter, and so we get, oh, not 0.20, I'm sorry, 0.40. There we go. There's our correct value. 2.19 is now our standard deviation. Okay. All right. So find the probability that exactly 8 of these 20 will have a part-time job. Now, when we calculate these probabilities for F, G, and H, this is where we use our binomial probability. We know it's binomial because we define 2 outcomes. Yes, they do have a part-time job, or no, they do not. So, if we say exactly, first of all, that tells us we're going to use the binomial PDF function, whereas in parts G and H, when it says at most or at least, we know there we're going to use the binomial CDF. So we know there's 2 binomial functions, and on the calculator we hit second and then the vars button right here, because actually we want the distribution. This is a binomial distribution. That's right there on the second level, so we hit second and vars. And then in this list, we'll scroll down to, now we have 2 options here, A and B. We have our binomial PDF, and we have binomial CDF. Now, so we know binomial PDF is what we're using for an exact value. In this case, 8, so that's x. X equals 8. All right, so if we go into our calculator now, hit binomial PDF, this brings up basically a table for us to fill out. We know it's 20 trials, 20 teenagers in this case. That's the sample size. Probability that they have a part-time job is 0.60. And we want to find the probability that exactly 8 will have a part-time job. That's our x. So we just plug that in, paste it, and enter. And so we can express this probability as a, let's go to 3 decimal places. So there'll be 0.035. Okay. Now, at most 6, that means x is less than or equal to 6. Okay. And the way that the binomial CDF function works for part G, okay, we'll go second vars, and I usually scroll up from the bottom because it's closer that way. So if you just arrow up, it loops through the list. So binomial CDF. Now, 20 trials, probability of success is 0.60. Those don't change. Now, x, so if we say at most 6, that's the way that the binomial CDF function works, because the binomial CDF goes from 0 to 6. That's what we'll find. Okay, which is what we want here, because at most 6 means we want to add up all those probabilities from 0 to 6, where x is 0, x is 1, x is 2, x is 3, 4, 5, and 6. And basically it takes 7 different binomial PDF calculations and adds them together to give us this binomial CDF calculation. But anyway, when we say at most 6, that means we just have to plug in 6 for x. Hit enter, paste, and enter. And so our probability is 0.006. This is pretty unlikely to occur. Now, we changed it up a bit in part H. So instead of saying at most, now we say at least. So in this case, x is greater than or equal to 12. Now the problem here is that the binomial CDF function can only find less than or equal to. Okay? So it worked perfectly fine for part G because we wanted x less than or equal to 6. We plug in x equals 6. Okay? But now, because when it says at least, we have to do this with the complement. Okay. Now, so we want the probability that x is greater than or equal to 12. Well, what is the complement of that? Well, if it's not greater than or equal to 12, that means it has to be less than or equal to 11. Okay? Because the opposite of 12 or more is 11 or fewer. And so this is what we can find now with our binomial CDF. And notice that we use x equals 11. Our first thought when we see this problem is that we're going to be using x equals 12. But the way that this at least probability works by using the complement is when we subtract that. Remember, this is 12 or more, so the opposite of 12 or more is 11 or less. So we have to use x equals 11 with our binomial CDF function. So we go back, second vars, and we want binomial CDF right there. Enter. So we have 20 trials. Probability of success is 0.6. And now we'll enter 11 for x value and paste it. And so that calculates that value as 0.404. But now we want 1 minus 0.404. And so 1 minus 0.404, and that gives us 0.596. So the probability that it's going to be 12 or more is actually 0.596, about 60% chance that that would happen. All right. Well, I hope that you have found this review helpful. If you have any questions for me before our test, just send me a message and I'll get back to you as soon as I can. So take care all, and best of luck.